Hi everyone. Welcome to our next video for week 7. And in this video, we're going to talk about making predictions. Once you have performed a test of significance and found that there is a significant linear relationship in the larger population, you can use your regression equation to make predictions about the population given an X or a Y value. So this is really where the power of correlation and regression comes in. Once we're confident that that sample is providing statistically significant evidence for a linear relationship in the population, we can use this regression equation to model behavior in the population. And that allows us to make predictions about given inputs or outputs. To do this, we're going to need to do some algebra. You're going to need to isolate the variable you're interested in finding. So if we're given an X value, we want to find Y, we need to get Y by itself. If we're given a Y value, we want to find X, we need to get X by itself. If you are wanting to find Y, meaning you're given an X value, you just use the regression equation as it is. It's already solved for Y. If you want to find X, meaning you're given a value for Y, you're going to have to do some algebra to solve that equation for X. So let's do some examples so that you can see how this works. And we're going to do this process really quick from start to finish. So example 1 says the number of fires and the number of acres burned are shown below. Find R and check that it is significant. If so, find the regression line equation and the number of acres burned when X equals 60 fires. So we see here we have number of fires X, acres Y. So very first thing we're going to do, we're going to run through this process, pick off our linear regression equation, pick off our R and R squared values, and then we're going to perform a quick test of significance. And if it is significant, then we're going to use that regression line equation to find Y, number of acres burned, when X is 60 fires. So let's go ahead and start this process. For this example, I'm going to use the TI-84. So I'm going to pull that back up. Very first thing we need to do is enter this data in. So stat, enter. I got to clear out the data from our last few examples. And then I'm going to start typing. So let's get that first few data points in. 72, 58, 47. I'm going to continue this process. I'll be back in just a second. So we can see here what the full data table looks like. You can see we've appropriately matched those points, 45 with 15, 57 with 30, and so on. And we know that we want our correlation coefficient. So we know we want R, we know we want R squared, we know we want that regression line equation, and we know we want to run a hypothesis test. So I'm going to set all of that up now because on a TI-84, I know that I can call one function that's going to find a whole bunch of stuff for me at once. So for our hypothesis test that we're going to run, null is rho is equal to 0. Alternative is rho is not equal to 0. I know to find my p-value, I'm going to run the lin-reg t test. And I know for that function, x values go in L1, y values go in L2. My frequency is 1, and my tail is a not equal to. And that's going to give us our p-val. And then we'll make our decision. And then we're going to skip step 4 based on our decision. Once we make a decision, we're going to know whether that relationship is significant or not. And then we can continue with the problem if needed. So let's go ahead and run that calculator program. So lin-reg t-test, we're going to go stat test down to the bottom, option F, and everything should be set up. X is L1, Y is L2. We go down to calculate. And first thing they give us, we see is that p-value right below the test statistic. So our p-value is 0.0253. And then I can see some information on that next screen. So I see the information for the regression line, y equals a plus bx. They tell me my a is negative 31.46, and that my b is 1.0. I'm going to round that to 4 since it gave us the other thing to 2 decimal places, x, a plus bx. I see my r squared, 0.5937 rounded. And if I go down one more, it should show me that correlation coefficient. And it does, 0.7705. So 7705, fairly strong, it's positive. So I'm fairly confident, at least in the sample, that we have a relatively strong positive linear correlation between X and Y. So as the number of fires goes up, the number of acres burned also goes up. To make a decision about whether that's significant in terms of the population, we have to compare that p-value to alpha. And we were not given one, so again, we're assuming 0.05. 0.025 is less than 0.05. So we're rejecting the null. So that tells us for step 4, and I'm not going to write a sentence, but I am going to say the relationship is significant. When we reject the null, that's what it's telling us. So what that means is I can use this equation that we found, y equals negative 31.46 plus 1.04x, to find the number of acres burned when x equals 60 fires. So I know that x is equal to 60. They've given me an x, they want a y. So I'm going to use this equation exactly as it appears. Y equals negative 31.46 plus 1.04x. And then I'm just going to make this substitution into the equation. Everywhere I see an x, I replace it with a 60. So y equals negative 31.46 plus 1.04 times 60. So let's go ahead and plug that into our calculator. I'm going to go back to the home screen, and I'm going to type it as it appears. And I get 30.94. 30.94. And I am going to attach units to that. And if I had room, I would write a solution sentence. I would say, based on our model, we expect that when 60 fires have occurred, that 30.94 acres will be burned. So that is the correlation and regression process from start to finish. We start with a raw set of data, we find the correlation information, we run the test of significance, and then if in steps 3 and 4, we determine that the relationship is significant, we make that prediction. Let's go ahead and try this process again and see what it looks like in GeoGebra. So for example 2, the average gasoline price per gallon in cities and the cost of a barrel of oil are shown below for a random selection of weeks from 2009 to 2010. Find R and check that it is significant. If so, find the price per gallon of gas when X equals $60 per barrel of oil. So we see oil as X, gas is Y. So for a 46.25 gallon barrel of oil, it costs $2.20 per gallon for the gas. So we're going to repeat this process using GeoGebra. And we know that first step is let's get our data in the calculator. So I'm going to go ahead and clear out everything that's here because we have a hot mess going on. And then I'm going to scoochie this over here. And we know that for GeoGebra, we give our list a name. I call it A by default because I'm lazy. Curly brackets, and then each of those ordered pairs. So 46.25, comma 2.197. And then I'm just going to continue separating those brackets with commas. I'm going to pause this and do it off screen and then come right back. Okay, so you can see that I've got this data here in GeoGebra. I'm going to minimize this for a second, clear out that data table so we have more room to work. And let's come back to GeoGebra. So we know for GeoGebra that we actually need to find our regression line equation, our R and our R squared separately before we run our test of significance, because those are each going to be unique function calls in GeoGebra. So let's start with R. We know that that's the correlation coefficient function call. And it says for that list of data, that's 0.9835. For R squared, I'm just going to take that value, which it saved as lowercase a, and I'm going to square it. So 0.9673. And then to get that regression equation, we're going to call the fit line function. And remember that it gives it to us out of order. We actually want to record that constant first. So 1.281 plus 0.022x. Now that we have that information, we can run our hypothesis test. So we're going to start the same way. We know what our null and alternative look like. Rho equals 0, rho does not equal 0. We know for 2 to find the p-value, first we have to start with the test statistic. So t is going to be r, 0.9835. And let me squishy down our GeoGebra screen so we have room to write here. And then the square root of n minus 2 over 1 minus r squared. Do the 1 minus r squared first, 0.9673 squared. And then I need to go back and look at how many data points I have. So let's go ahead and do that. 1, 2, 3, 4, 5, 6. I'm counting 6 ordered pairs. So this again is going to be 6 minus 2 on top. And then we're just going to plug that in GeoGebra to get our answer. And then 6 minus 2 is 4. 1 minus 0.9673 squared. And that gives us 7.755. And I made a boo-boo on the last page and nobody called me on it. We'll go back and fix that in a second. So I'm going to run that t-distribution. So we know that that asks for degrees of freedom, and then our test statistic. Nobody called me on that either. 7.755. And I'm going to do a trick because I know that that's positive. I know I'm going to need the complement because it's finding the area to the left. And I know the t-distribution is centered about 0. So 7.755 way up here, it's going to give me all of this. I don't want all of that. I want what's in this tail. So I'm going to do 1 minus the t-distribution. And it gives us 0.0007. And that tells me my p-value is going to be twice that. Didn't make a mistake because PI does that by automatically, and I forgot. So pardon my brain farts. So we're going to take this number and we're going to multiply it by D. So, or 2, sorry. So 2 times D gives us 0.001489, so 0.0015. And you'll notice that makes a difference if you do the variable times 2 versus 0.007 times 2. If we doubled the rounded answer, we get 1.4 instead of 1.5. So again, if you're seeing small differences, that's rounding error. So we've got our alpha, 0.0015. We know not our alpha, our p-value. We need to compare it to our alpha, which when not given is 0.04. Oh, 05. Oh my goodness. I am so sorry, guys. Bear with me. We're almost there. P-value to our alpha, 0.05, and 0.0015 is way less than 0.05. So we can confidently reject our null, which means that there is a significant relationship. That relationship between X and Y is significant. What that tells us is we can use that linear regression correlation to make predictions about the population. So in this case, we're told that barrels of oil cost $60 a barrel. And they want us to find how much does gas cost when oil costs $60 per barrel. And we know that the cost of gas Y is equal to 1.281 plus 0.022 times the cost of a barrel of oil. So just like last time, we're going to, everywhere we see an X in the formula, we're going to replace it with 60. So 1.281 plus 0.022 times 60. And this is definitely something we're going to need a calculator for. Pull this over here. So down on the bottom, 1.281 plus 0.022 times 60. And I don't know if you can see that, but we are getting 2.601. 2.601. And I should interpret that. First, I know that it's going to spit out price per gallon. So at $60 per barrel of oil, we expect gas to cost 2.601 per gallon. So again, this is the linear regression process from start to finish. We started with raw data. We calculated the correlation coefficient, the coefficient of determination, and the regression equation. We used that information to perform a test of significance. Is there a significant relationship in the larger population based on this sample data? And when we found that it was significant, we then used our regression equation to model behavior in the population by making a prediction. Okay, if you have questions, I have office hours this week, Tuesday, Thursday, Friday. You can always reach me via email. Uh, I hope you're having a good last week of the course, and I will see you in our next video.